All right, welcome to Engineering 270 Lecture 11. So this is the beginning of week 6. So today we're going to talk about A to D conversion. This is probably our final subsystem that we're going to talk about inside the PIC processor. By subsystem, I mean a collection of hardware inside the chip itself that does something for us. For example, the input-output modules, the timer modules, the pulse width modulation, those kinds of things. So A to D conversion is another set of hardware inside the PIC. It's another set of registers we want to deal with, and it does a very useful function for us. It lets us feed an analog voltage to the pins of the PIC processor and figure out internally what that voltage is. For example, everything we do in digital is generally either 0 volts or 5 volts. And 0 volts is considered a 0, 5 volts is considered a 1. And if you have a digital input pin and you put, say, 4.2 volts into that pin, and you do an input from that port and you look at that bit, you're probably going to see a 1. And if you put in a 1.1 volts, you're probably going to see a 0. But you're always going to see either a 0 or a 1 because it's digital. But what if you actually care what's the actual voltage? I want to actually know that there was 4.2 volts or there was 1.1 volts. That's where an A to D, an analog to digital converter comes in handy. Why do you want to do this? Well, typically when you're working with sensors, so you have a temperature sensor and you want to know more than just the temperature is high or low. You want to actually know how many degrees Celsius. And that gets translated into a voltage, say between 0 volts and 2 volts. And the more accurately you can measure that voltage, the more precisely you know what the temperature is. So again, an A to D conversion will be useful for us to convert this analog voltage into a number that we can analyze. So here's a picture from the data sheet of what a typical A to D system looks like. And the main things to note here is that this is an analog voltage source. Okay, so this is some variable voltage other than just high or low. This is an analog input pin on the PIC, AN0, AN1. There's a total of 7 pins up through AN6. And this is all magic stuff inside the chip. But basically, there's a capacitor here. And if you looked at capacitors in 120, when you put a voltage on a capacitor and then you disconnect the end of that capacitor, it tends to hold the voltage for a little while, right? Capacitors hold charge basically. So a signal comes into the analog pin, and effectively when this switch gets closed, that capacitor charges up with whatever voltage is coming in, and then when the switch is opened, that charge will be held in this capacitor for a brief period of time. And this is the thing that's actually sampled by the AD conversion system. So this is called sample and hold, right? You close this switch, send some input in, that gets sampled. When you lift this switch, so this is disconnected, that's the hold. And once you're holding that input voltage, well, now this thing called an A to D converter reads that and basically converts it to a digital number. And that digital number gets stored in some file registers. And now you can process those file registers and see what the voltage was. All right, so how do we interact with this? Well, we use more file registers, and there's 3 file registers mainly that we're going to use to interact with the A to D subsystem. So ADCON 0 is a configuration register, 8 bits like all file registers. The 2 most significant bits, vconfig 1 and 0, that basically chooses what voltage range we're going to use in our conversion. So here's the basic setup. Suppose you have a signal which is, analog in nature, and it's changing from 0 volts to 5 volts. Okay, so we want to convert this into some sort of digital information, and this is a 10-bit A to D converter. So we might say that 0 volts corresponds to all zeros, and 5 volts corresponds to all ones. Okay, but now suppose we have another signal coming in, and this signal only varies from say 0 volts to 0.4 volts. Well, if all zeros is 0 and all ones is 5, then the value for 0.4 volts is going to be pretty small, right? We're not going to be using this full 10-bit range to represent all the values that we expect to see. So we would like to calibrate the system and say, okay, 0 volts is going to be all zeros, and maybe 0.4 volts is going to be all ones. So now we've got a full 10 bits to represent every voltage level between 0 volts and 0.4 volts. And the understanding is we're not going to put in anything bigger than this, because if we did, we'd need to convert it to a number bigger than all ones, and we can't do that with just a 10-bit number. So we need to specify this voltage range, and that's the purpose of this ADCON 0 register upper 2 bits. So we specify what the positive and negative voltage ranges are, the highest and the lowest, and we have choices. We can use the power supply. So if those bits are 0, 0, then our voltage range is, in our case, from 5 volts to ground. Or we can specify an external voltage for the upper value and use ground for the lower. Or we can use the power supply for higher and an external reference for lower, or external references for both higher and lower. So if you wanted to only work with voltages between, say, 0.7 and 1.3 volts, we could set an external positive reference of 1.3 and negative reference of 0.7, put these 2 bits to 1, 1, and then we'd be converting between that range. Bit 5 is not used. Bits 4 through 2 are used to select which of 7 channels we want to convert. So there's 7 analog input pins, and we can have 7 different analog voltage sources connected to each of those 7 pins, and we can choose which one of those we want to pay attention to and convert to a digital number. So these 3 bits, channel select 2, 1, and 0, choose one of those 7 channels. And these are labeled AN0, AN1, AN2, and those are simply pins on the outside of the chip. So if you look at the pinout of the chip, right, here's AN0, here's AN4, 3, 2, and so on. So we can hook up voltages to all those different pins, and then we get to choose in software which one we want to actually read. So that's what the channel select bits specify. We turn the whole thing on with bit 0, that's the on-off bit. 1 turns it on, 0 turns it off. And then to start a conversion, we set bit 1 to a 1, that's the go signal. And it will remain at a 1 until the conversion is finished. Now the conversion takes a certain amount of time. So when the conversion is finished, the system will change this bit to a 0. So how do we use this? Set everything up, write a 1 to this bit, and then monitor this bit until it's a 0. Once it's a 0, we know the conversion is done and we can read our answer. Of course, like everything else on the PIC, we can also configure it to throw an interrupt when the conversion is finished. And then we don't have to poll this pin. We can start the conversion, go off and play games or whatever, and when the conversion is done, we'll get an interrupt, and our interrupt code can respond to that appropriately. Okay, so that's ADCON 0. Next register, ADCON 1. You've heard about this register before, right? You always put 7F into it. Well, what do these bits do? If you put a 1 in each of these bits, it says, I want this bit to be a digital input or output. If you put in a 0, you're saying, I want it to be analog. So when we load 7F into ADCON 1, we're making all these bits 1, which means we're saying every pin is a digital port. It's either digital in or digital out. If you put a 0 in, say, bit 0 over here, we're saying we want AN0 to be used as an analog channel. And AN0, remember, you find this on your pin diagram, that's pin 1. So once we clear bit 0 of ADCON 1, this pin is no longer digital pin RA0. It has nothing to do with bit 0 of port A or latch A anymore. It's only used for analog input. And it basically feeds into the A to D converter. Alright, so that's ADCON 1. ADCON 2 is a little bit weird, so we're not going to worry about this too much, but basically bits 5 through 3 specify how long you want the system to wait to acquire a signal. This basically matters if you have a signal that's changing very rapidly. You need to tell it how long should it sample the signal before beginning the conversion. If you were to do this with just a signal that changes very slowly, you could just load all ones into here. That makes the acquisition time as large as possible. So once you say go, it will wait a certain amount of time, analyze the input signal, and then it'll go ahead and start the conversion. Conversion clock, similarly, for us, we could set it with a slow system clock. We could set it to pretty much any of these values, 110, but again, if the input is stable, you can set it to all zeros, and that's a very slow conversion clock, but if we're not really worried about speed, that's fine. If you look in the data sheet in this chapter, this is chapter 17, there's lots of verbiage and complicated formulas and physics speak about how to set these things up based on signal characteristics, temperature, all kinds of crazy things. The one bit we do really need to worry about in here is bit 7. This says how should we justify the result, because remember our converter is doing 10-bit A to D conversion, which means when we convert our number it's going to look something like, well, I won't fill in ones and zeros. Yeah, well, it's going to look something like this, 10 bits. Our file registers are only 8 bits, so we're going to use a pair of file registers to store this. Well, there's two possibilities. One possibility, store the low 8 bits in one file register, and then store these 2 bits followed by a bunch of zeros in the second file register. The other possibility is to store these upper 8 bits in one file register, and then store the lower 2 bits followed by a bunch of zeros into the other register. So this is AD result low, and this is AD result high. And the same thing here, low and high. This is called left justified, and this is right justified. What's the difference? Well, basically, if we do this and we don't really care about these 2 least significant bits, we could totally ignore AD result low and just look at AD result high and treat this as an 8-bit A to D. But if we're actually doing 16-bit things and we want to treat this as a 16-bit number with leading zeros, we really want it to be right justified, so we would probably want to store it like this. But again, it's not really critical for us, and we don't use the A to D converter in any of our labs. It's just something I want you to have seen and have heard about the basic concepts of. So that's really all there is to setting up the A to D conversion. And if you, so there's the scary equations and stuff for figuring out acquisition time and so on, and the tables and so on and so forth. And if you look at the summary of A to D registers, there's a whole bunch of registers involved here, right? Interrupt registers, AD result high and low, 3 control registers, and then of course the port, tris A, and latch registers that are involved in anything that we're doing with any of these pins. So we'll have some homework problems to go ahead and set these things up, just to sort of play around with these concepts a little.